Hello everyone, my name is SongyangLiu. This is my final report presentation for my class, and this is the first part. I will do an introduction to my PowerPoint file, and the name of my project is Performance Analysis of Different Fading Channel Models. And my project is divided into 5 different parts. The first part is the introduction. In wireless communications, fading is variation of the attenuation of a signal with various variables. These variables include time, geographic position, and radio frequency. Fading is often modeled as a random process. A fading channel is a communication channel that experiences fading. In wireless systems, fading may either be due to multipath propagation, referred to as multipath induced fading, whether particularly rain, or shadowing from obstacles affecting the wave propagation, sometimes referred to as shadow fading. And the second part of the paper is description. In this project, my target is to implement a slow fading channel for both flat fading and frequency selective fading, and compare the performance of these two channels. And this description often is also divided into 4 parts. The first part is channel estimation. There are 2 main categories for channel estimation. The first one is plot-based estimation, and the second one is the blind estimation. For this project, I decided to use the first one, plot-based estimation. An adaptive equalizer is an equalizer that automatically adapts to time-varying properties of the communication channel. A lot of different algorithms can be used for these models. For this project, I decided to use LMS, least mean squares, and RLS, recursive least squares. And the least mean squares algorithms are a class of adaptive filter used to mimic a desired filter by finding the filter coefficients that relate to producing the least mean square of the error signal, which means the difference between the desired and the actual signal. It is a gradient descent method in that the filter is only adapted based on the error at the current time. And the recursive least squares is an adaptive filter algorithm that recursively finds the coefficients that minimize the weighted linear least squares cost function relating to the input signals. This approach contrasts with other algorithms such as the least mean squares that aim to reduce the mean square error. In the derivation of the ILS, the input signals are considered deterministic, where for the LMS and similar algorithms they are considered stochastic. Compared to most of its competitors, the ILS exhibits extremely fast convergence. However, this benefit comes at the cost of high computational complexity. And the second part is about the gray coding. The reflected binary code, also known just as reflected binary or gray code after Frank Gray, is an ordering of the binary numeric system such that 2 successive values differ in only 1 bit, which is a binary bit. And the third part is the introduction of the flat fading channel. In flat fading, all frequency components get affected almost equally. Flat multipath fading causes the amplitude to fluctuate over a period. In flat fading, the coherence bandwidth of the channel is larger than the bandwidth of the signal. Therefore, all frequency components of the signal will experience the same magnitude of fading. And the final part is an introduction for the frequency selective fading channel. The selective fading or selective frequency fading refers to multipath fading when the selected frequency component of the signal is affected. Selective fading or frequency selective fading is a radio propagation anomaly caused by partial cancellation of a radio signal by itself. The signal arrives at the receiver by two different passes, and at least one of the passes is changing. This typically happens in the early evening or early morning as the various layers in the ionosphere move, separate, and combine. The two passes can both be sky wave or one be ground wave. And the third part of the paper is channel parameters. And the first section is the frequency parameter. For the frequency parameter, I decide to select GSM as the channel environment. Therefore, the bandwidth for each channel should be 0.2 MHz, and the carrier frequency should be 1.8 GHz. And the second parameter is the modulation type. This simulation is based on the baseband simulation, and the Matlab program I found on the internet can support two data sources, namely randomly generated data or just image files. Although random data is very suitable for testing BER performance and the influence of the channel on the signal constellation, the image file provides us an intuitive impressions and comparison of different channels. In this channel model, I use phase shift keying modulation to modulate the data source, and the user can select any memory PSK to modulate the signal. For this project, the default setting is QPSK modulation. Users can also choose whether to use other modulation types as 8PSK in the simulation. And for the encoding parameter, for this project, user can select use the gray code or not for the encoding setting of the channel environment. Normally, I decide to use the gray code encoding. And this part is about the percentage of training data length. Estimation of the channel phase for each coherence time is necessary since this model uses PSK modulation. For this project, the default value is 8% of the total data length. The handler of the source data is inserted for each coherence time. This parameter can be used to estimate the random phase shift of the fading channel and to train decisions to adjust the received signal with phase recovery. We will see that effect in the later part. And this part is about the velocity. The range of the velocity is from 20 km per hour to 120 km per hour. The default setting is to use 20 km per hour as the user's velocity. For the minimum value 20 km per hour, I can calculate the TC is much larger than 300 nanoseconds. So this channel is a slow flat fading channel. For 120 km per hour, I get that TC is still larger than 300 nanoseconds. So the channel is still a slow flat fading channel. And about the equalization algorithm, in this project, I use LMS and RLS to produce an equalized object in Matlab program. The radio channel characteristics and the intended use of the subscriber equipment is a key issue for the performance of equalization algorithm. The velocity of the mobile user determines the channel fading rate and the Doppler spread, which is directly related to the coherence time of the channel. The choice of the algorithm and its corresponding rate of convergence depends on the channel data and coherence time. And this part is about the channel estimation mode. In this project, user can select the model without reset result from last coherent time or reset result from last coherent time. If user chooses to reset the result during each coherence time, equalizer will reset the state of the equalizer come from training result of last coherence time. If user chooses not to reset, The equalization process just uses the result of the last coherence time. And this part is the simulation and the result. I will discuss the simulation result with 3 parts. First, in order to test the performance of frequency selective fading channel, I transmit an image file through this channel and observe the image quality after transmission. Another criteria is BER, which can be used to compare with channel theory. Second, in order to test the performance of a flat fading channel, I also transmit an image file through this channel and observe the image quality after transmission. Another criteria is BER, which can be used to compare with channel theory. Last, I analyzed the performance by comparing 2 different channels under the same parameter setting. All the simulations are based on QPSK modulation with Greek code. And the first part is about the frequency selective fading channels. We need to do the comparison of BER. As shown in the figure 1, the BER performance of transmission through frequency selective fading channel is not good as the BER according to the theoretic analysis. For the reason, there is one important assumption about the BER theory. That is, the user should already know the phase information of transmission signal. But since the transmission channel is time variant, the estimation error is inevitable for phase information. And second, we need to do the comparison of image quality. In figure 3, the received image is of pretty low quality. Random noise and block noise can be observed in the image, and the overlaps can also be seen in the image. For the reason, the phase estimation error will take over with white Gaussian noise in the transmission channel. Another point is that inter-symbol interference will also occur due to frequency selective fading channel. And in the figure 4, the figure shows the effect of equalization algorithm, which improves the image quality greatly. And the second part is about the flat fading channel. We first need to do the comparison of BER. As shown in figure 5, the BER performance of transmission through frequency selective fading channel is not good at BER according to theoretical analysis either. The reason is the same as frequency selective fading channel. Another point is in the situation of low SNR. The BER performance is relatively close to theoretical analysis, while in the situation of high SNR, the performance is worse. And second, we need to do the comparison of image quality. In figure 6, the received image is of pretty low quality as well. Random noise and block noise can be observed in the image. For the reason, it can be that phase estimation error occur in a coherence time. And in figure 7, the image quality is greatly improved due to the adjustment, which occurs by adjusting the received signal with phase recovery, which we mentioned earlier. And the third part is to do the comparison between these 2 channels. And for the comparison of BER, as in figure 1 and figure 5, the BER performance of flat fading channel is slightly more favorable than performance of frequency selective fading channel, and this phenomenon is just as predicted by theoretical analysis. And second, we need to do the comparison of image quality. According to figure 3 and 6, the received image quality is both pretty bad in flat fading channel and frequency selective fading channel. However, the reasons for 2 channels are slightly different. In flat fading channel, the image is affected by random noise and block noise, and in frequency selective fading channel, the image is affected by random noise, block noise, and overlap. And the conclusion for the final report is that in this paper I built and implemented 2 different channel models, which is flat fading channel and frequency selective fading channel with transmission of same image. And I also do the analysis and comparison between these 2 channels. and the result is pretty similar with the theoretical analysis. Thank you for watching. And the second part of this video is to do the presentation of the computer algorithm. And this part is the Matlab program. I need to run the script and let me show you the process of this program. And I need to select the modulation type, and the default setting is QPSK. And I would like to use Greek code. And let's say we select the flat feeding channel in this video. And the default training data length is 8%. And the dB for plot is also in default. And the velocity is defaulting 20 km/h. And I would like to transmit the image file over this channel. And this is the result part. The Matlab will show the original image and the transmitted received image as well. As the program is plotting the constellation, there are 122 times of iteration, so it may take some time. And this figure 2 is the received image, and this figure 3 is the adjusted image, and figure 4 is the BER performance. Okay, that's the end. Thank you for watching.